Ah, okay. Okay, good afternoon, everyone. So we are back at the first workshop on macroscopic quantum phenomena. And it's a pleasure to introduce Dr. Rocío Jauregui. So Rocío, she's a very UNAM person. She made her undergraduate, master, and PhD here at UNAM. Then she did a postdoc at Barcelona, right? And then she came back to Mexico, and she's a full professor here at Instituto de Física de la UNAM. And today she will be talking about upper bound for the duration of a quantum jump. So let's listen to her. Thank you, Rocío.
¿Ya?
Okay, yeah.
¿Ya se escucha? Sí. Okay. Good afternoon. It is a pleasure to be here, and I want to thank Jorge because all of the effort to bring this workshop. I will talk about the quantum direction of a quantum jump. It is not exactly the type of things we have been listening in the last talks, but nevertheless, it is quantum, so I hope you can find it interesting, okay? The idea goes as follows. When one talks about quantum jumps, one can imagine the idea or board behind it. And what we wanted to do is to see if it was possible or not to establish an upper bound for the duration of a quantum jump. That is it is very, very simple idea. The main points are, I think, quite trivial. And what I want to say first is that we are not saying that the things I will describe give the best that can be done, but I can say that it is the first time, the only experiment I have found, where this is the main goal. I want to know whether a quantum jump is instantaneous or not, to the degree of actual, nowadays, limits. That is the only point. I will not do anything very complicated. It will be very simple. The description, the theoretical description, it is also very standard, and I will try to make you feel what is the limits in the theoretical world and what are the limits in the experimental world, and perhaps someone can do this better in this moment, but they haven't asked the question. Okay? So the only point is I want to know whether one can measure or not the duration of a quantum jump. It is simple, nothing more. The first part of the talk refers to the quantum jump. ¿Acá es mejor? Ah, mira, y mi vida cambió. Muy bien. The quantum jump notion, I will talk about the things you have learned in the school, no? Then I will describe the system we will be working in. I will do the calculations, the standard, really standard calculations. I will describe the experiment that was taken in Singapore, and I will put ideas about the perspectives. What can one expect from this, okay? So, in 1913, before quantum mechanics, Niels Bohr made a construction of the old quantum theory. His idea was to reproduce the emission of the atoms, the light that was emitted by the atoms, and he proposed it just as a proposal. He was a student, in fact, it was his PhD thesis, that perhaps the atoms can stand just in given states, and that the light is the result of the transition from those given states, and that each atom had preferred states that distinguish one atom from the other. Those ideas were correct in the sense that they were observed, and he just made a formalism, very clear, very clean formalism. And the point that he wanted to, for the reason that he introduced the jumps, is that in his model, the atoms could exist just in the energy levels, in the correct energy levels, depending on the It was just a hydrogen atom, but it doesn't matter in the first attempt. The atoms could just be in a given state, and if they could just live in a could exist just in a given state, when they go from one state to another, these states are not allowed, so the jumps, the transition from one state to another should be instantaneous. And he wrote, this should be instantaneous, and so I will call it quantum jumps, okay? Later on, in 12 years later, 13 years later, the quantum theory was formulated by Schrödinger, and Schrödinger introduced, as you know, wave mechanics, and later, in 1952, he wrote a paper asking, are there quantum jumps? After 40 years, after 26 years that the quantum mechanics was formulated, is it true that we have to still talk about quantum jumps? And he wrote a paper where many ideas regarding the collapse of the wave functions are discussed, and he didn't feel comfortable with that, to the degree that he started questioning the idea that even particles exist. So he says, particles may not exist. They probably are just wave packets and nothing else, or what is happening. He was very, very confused. And in the paper, in fact, he was trying to describe what people see in the particle physics see in the las cámaras de niebla, how to say? He says, I want to understand the tracks, and I would like to understand that in terms of the collapse of the wave function, but that is not okay compared with what one observes in the case of wave mechanics. So I will say that particles are just wave packets, and particles do not exist. And there is a school nowadays here in the States saying that particles don't exist, that you just can work with wave packets without talking ever about particles and about many things, okay? Later on, in 1986, Bell wrote a paper with the same title that Schrödinger used. He also asked, are there quantum jumps? The question is the same, and he starts saying, yes, I'm writing this paper taking the title that Schrödinger did in his paper, because I want to discuss the same things, but from another point of view. And he says, yes, quantum jumps may exist, and he makes a very strong criticism to the people that were working with hidden variables, and he said, yes, quantum jumps may exist, and perhaps they can be properly described, not as instantaneous things, but things that take some time to be realized. And he in that papers gave a strong support to a theory that I will not want to discuss because I don't work on that, that extends Schrödinger equation in a nonlinear way and gives bounds to the duration of quantum jumps. And this theory was formulated by people also from the particle physicist community, and the papers are there, but I will not want to talk about that. I just want to give the idea, okay? So quantum jumps were just a formulation, something that people did not observe directly, until in the same year that Bell wrote his paper, Delmet proposed to give a configuration, in a spectroscopic configuration, where you could observe the jumps. The idea is very simple, and this gave rise to a whole spectroscopy field, no? That is the Shelby configuration. In that configuration, you use a laser that sends one atom to a given transition, yes? But sometimes you can make a transition to this level that has a very, very long living time, okay? And when the atom is not making this transition, the atom is on this transition. And the idea was simply to solve the jump in terms of not observing something. So you have a short-lived transition in the standard range, 9 nanoseconds, and a very long transition, and sometimes the atom is put in this shelf, goes here, and so you don't observe this transition. Okay? And these are the results that they found. It was two groups, the Tosche group and the Wineland group in the same year. Wineland was studied with Delmet, so he has all the school of Delmet, and he did very, very well. And the idea is as follows. Here you observe transitions, and when you go to the forbidden transition to the metastable state, you stay here until the atom starts going here and here and here and here and here. So when the transitions take place, you're here, and the dark zones correspond to the time that the atom is in the other state. And here you can observe that the passage from dark from bright to dark is very, very, very sharp. The only point is that the scale here is seconds, so that this experiment is not a good experiment for observing how long a transition, the jump takes place. But what you can try to make the statistics is how long the atom stays in a given in the dark or the bright region. Okay, so in the 1986, the experiments were performed. Quantum jumps were observed, but the important question they were interested in knowing how long will you have to wait until you go to the dark region, and how long you have to wait until you go to the bright region. And this gave rise to a very, very interesting analysis in the theoretical world. Another important point to mention is that whenever an experiment was performed with, these experiments were performed with ions in traps, that is in general the idea of Wineland, and were performed with a single atom in a Paul trap, and the observation corresponds to that single atom. Okay, these experiments, in general, whenever Wineland made an experiment for ions, Harosh made an experiment for photons. And you can always look at, and they are very good friends, and they go together, and they decide things like that. But in the problem of quantum jumps, instead of publishing everything together, in this case, Harosh took almost 20 years to achieve the analogous experiment for quantum jumps in the realm of photonics. Okay, so it was very, very difficult to observe the quantum jumps, and in this case, we're 20 years later, but the idea is the same. You observe something happens, and then something different happens, and something happens, and something different happens, and the jumps occur here, no, in a given time. Okay. As I was telling you, Cohen and Dalibard performed very interesting calculations about the waiting time distribution. That is, how long you have to wait until a jump takes place. And in this context, they noticed that the important ingredients for constructing a theory for the waiting time distribution was to take into account the most important time scales of the problem. In general, they assumed that one jump is completely uncorrelated to the previous one. That is a Markovian assumption. And they also developed in the same years, from 82 to 86, 87, they developed the theories of photon counting, okay? How a photodetector works, how many things you have to assume about the detectors when you do photon counting, and many interesting things arose. So in general, they were worried about the time you have to wait until a jump takes place. They made the theory, and they got good results. Photodetection theory, as I told you, was also developed in those years, and they made a clear analysis of how a quantum system should be conditioned when you get a measure from a given detector. Okay. Photodetection theory and the idea of how long you have to wait to see something gave rise to the Monte Carlo wave function method in quantum optics, simultaneously by Dalibard and by Carmichael in New Zealand. So both theories are very interesting, and in the last year or this year, I don't remember, they made a very interesting experiment about whether you can or not manipulate the quantum jumps, in the sense to know, to have expectative of when a jump will occur, and if you have expectative of when it will occur, whether or not you are able to manipulate time so that the jump doesn't take place, okay? And this experiment was performed 2 years ago and reported this year or last year, and nevertheless, it's not exactly my question. My question is know how long do I have to wait until a jump takes place. My question is how long a jump requires to occur, okay? So these theories are very, very nice, but in all of them, the jump is assumed to be instantaneous, okay? They occur at random. They require to describe what happens of a non-Hermitian Hamiltonian, but the jumps are instantaneous, okay? Okay. As I told you, that is the theory of GRW that refers to making a theory to know whether the collapse is instantaneous or is not, or how long it takes, okay? So after all this I have said, the important point is that I consider that, I know it is not my point, but it is not just me. The quantum jump is a relevant one, and we should not forget that. And the consequences and interpretation is not so clear. And I think that it is a good time to ask whether this can be done better, whether we can study the structure of the rise and descent of the transition. Is it possible or not? Now that detectors of time are able to resolve 1 second in the age of the universe, we should be able to resolve how long a quantum jump takes place in a given experiment, okay? So I look in the literature and I couldn't find any experiment that gave me a limit on the jumps. Okay, and so I think that it is important, and I convince someone to try to do just a first attempt to measure that. Okay, okay. And this experiment, the experiment we propose refers to four-way mixing in atomic gases. I will describe this, and the important variable that I will be interested is the two-time correlation function that has a discontinuity that is always assumed to be due to quantum jumps. So four-way mixing in atomic gases in general correspond to the idea of introducing two lasers and getting a parametric conversion of this light into other photons with different properties, with different momentum, with a different frequency, okay? So you have an atomic cloud, two lasers in seed are directed to the cloud, and you get two photons, okay? In our case, we are the standard one. It is just rubidium as usual. And you make the transition from the ground state to the first excited state, then to another state. These are the two lasers. And here you have the two spontaneous decays, okay? The four-way mixing in this configuration is expected to be described by a time correlation function where whenever you see a signal at time t, s, you will observe an idler, that is another photon from this transition, with a probability with this form, okay? So at time t, in this case it would be 0, you observe a photon from here to here, and then you have to wait that the second transition takes place, and in general you expect, at least in the in standard Weisskopf-Wigner approximation, exponential here, and what I am interested is not in the exponential. I am interested in the op of this exponential, because this should be a limit. This line should correspond to the limit of the time it is required to go from here and to here. Okay? So the idea is clear. I send, well, not me, but someone sends 2 lasers. It's an atom cloud. The atom goes here, and then it has to go here and here. And whenever I observe this, as I ask how long I have to wait to observe this, and I expect something that is like this, an exponential, and my question is how long, or how this step is right, or is a little bit with an inclination that give me a time, an upper bound for the duration of the jump. That is the question, okay? Okay. Then theory, okay? In theory, you are interested in observing 2 photons, the signal and the Idler, that is the first photon and the second photon. And the G2 function, the coincidence function, is the expectation value of the state for these operators that are just the creation and annihilation for the photons with a given frequency, okay? In the process, for the process we are interested in, this element is proportional to this element that give me the coherence that I go to from 2 to 3, and then from 3 to 0. I just remember 3 is 1. From 2 to 3, and then from 3 to 0, okay? That is, these photons are emitted when this coherence have a given value, so this factor is proportional to this factor. If I use a standard formalism, I can work out this element and find that this element is proportional to the population of level 2 at time t, and the population of level 3 at time t plus tau. The important point is that this density matrix element corresponds to the population of type 2 with the initial condition that could be, for instance, that initially the atoms were in the ground state or anything, that is the standard one. And the second term, when you do the calculations, requires that initially the atoms, this G33 is not identical to this. These populations refers to it has as initial condition that the atom was originally at the position 3, okay? So these are not the density, the standard, okay? Of course, you can use the regression theorem, or you can do just some algebra and get the result, okay? This is just to show that it is possible to show it without doing anything spectacular, okay? So for the description of the system, we put the master equation, the standard master equation, the standard Hamiltonian, the standard that is the atoms that can be in different levels with a given energy h omega L. You have the light that has been that refers to the different photons, and when you make the coupling with the lasers, you can substitute this by classical waves, and that is the reason here I don't have operators, because I am using that they are coherent states, so I have the Rabi frequency for classical light, okay? And the emission is taken as in the standard case that corresponds to using a Lindblad equation, where here you introduce the standard results, okay? That is, this is spontaneous, and these terms correspond to the inverse of the decay rate, and you can include, or not if you want, Doppler-Rodering effects in different terms, okay? So it's the standard, really standard, okay? We worked in the interaction picture and consider that we didn't want the atoms to stay in this level. So the standard trick is to send the light without giving the tuning, so that the atoms do not like to be here, and then send the other almost resonant with this level, the second laser, to guarantee almost resonance to maximize the population on 2, because I want to have a lot of atoms here, and so I have to make this, okay? So, okay. In this case, we can do the standard adiabatic elimination of the system, of the 2 level, and simplify the master equation, and solve it in standard, really standard. I just want to show that I am not doing anything strange. That is, after eliminating the first level, the density matrix has this equation, and we can solve it using Laplace transform and get analytic results for the calculations, okay? So it's the master equation, Lindblad, that is spontaneous decays, and with the correct boundary conditions. We did that with the effective 3-level system, found the analytic expression for the elements, and got the solution of the time evolution of the population of the second state that I need for calculating the correlation function of the photons. Okay, that starts in 0, oscillates, and if you wait a little bit, it will converge, and almost half of the time the atoms will be in this state. Okay. At the short times, one can show that, okay, you start in 0 and then it oscillates, okay? For the other matrix element, when you make the calculations, it gives you directly that there should be a step function that is 0 here, and then when the transition takes place, here you have a really theta function, and then it decays, okay? If you look at incidentally, if you look at the results, here you have small oscillations, and these oscillations have not been explored too much, but they are there, okay? The experimental setup, the experiment was performed in Singapore, and here they used a rubidium cloud, the pump, they send the 2 lights, no, the 2 excitation light, then observe the Irler and the signal photons here. So it is really, really a simple experiment. This is not too complicated. Okay, we made it in the Instituto de Física because here we have everything, but we don't have enough expertise to guarantee that you are doing as much clean as we would like concerning the results, the numerical results. No? When you make the measurements, the results are here. These are the coincidences. The time scale, you can observe this in the scale of nanoseconds. If you compare this with the experiment of the quantum jumps, in that case the scale was seconds, and that's why we didn't try to do with that system. But here you have something that goes up, down, and then oscillates. If you look carefully at this region, you have this, no? This inclination. Okay, we are not saying that this is the duration of the quantum jump, because we know that the detectors have a certain time of response. So you have to take into account the experimental calibration of your detectors, and take away the effects of the finite time for detecting. Okay. To that end, the student that did this experiment considered an SPDC process. That is, he went to another lab and saw how long the spontaneous parametric down conversion, the response for the coincidences in an experiment of spontaneous parametric down conversion with the standard BBO crystal. And they found that this was consistent with a response of 0.1 picoseconds. Okay, so I know that the detectors are of the latest generation, and I believe in the care the student took to get this resolution, okay? When you take into account these facts, that the detectors have a finite time of response, what you obtain is the same graph that we had before can be compared with the error can be subtracted, the effect of the detector can be subtracted, and now we see something that is more steep, but we, in this case, we find a certain time of response, and we consider that this gives us that for the experiment under consideration, the duration of the quantum jump is about 0.03 nanoseconds, okay? So we are giving an upper bound. We are not saying that we have measured how long a quantum jump takes place, but we consider that this is a limit, an upper limit of how long it should be, okay? Now, so in this experiment, an upper bound for the duration of the quantum jump was measured, and this value is 3 orders of magnitude shorter than the natural lifetime of the involving atomic states, and nevertheless, it's 4 orders of magnitude longer than the optical cycle. That is, we are not able yet to work on the limit of the uncertainty relation of time and frequency, because the optical cycle continues being 4 orders of magnitude bigger than the bound we are giving. So we think that this should be improved, okay? There is no fundamental limit to the time resolution using this method, but up to the scale of the photoelectric effect, no? Because the detectors will always have a limit on that. And a suggestion made by the person that the professor in Singapore is that perhaps it would be better to consider another kind of detectors, in particular the nanowires, superconducting nanowires, probably improve this measurement. Okay? So the idea, I insist, is not to say that we have measured the duration of a quantum jump. The idea is to introduce to the community the point that it is possible to explore this system, and that it would be interesting to explore this, to learn more about quantum mechanics. That is the only message. You are not saying, no, this is the best and we have done the best. No. Perhaps you, the experimentalists, can do something better. Please do it, and we will learn, no? Okay? Now, from my side, what kind of things I can do better in the theoretical description? Of course, I can try to describe the quantum bits, that is the oscillations that you observe here, these oscillations. I can try to describe them, and in fact, not just I can, but already have done. We have introduced the system, and I will tell you what are the origin of the quantum bits. And we have also shown that there are, beside the quantum bits, other source of oscillations in the decay curve. That is, the decay curve cannot be exactly the Wigner-Weisskopf. The calculations give you some corrections to the Wigner-Weisskopf decay, and this we have found. And we have been learning about collective effects because this experiment was not performed with a single atom. I must tell you that the first time I suggested this experiment to the people in Singapore is because they have done some experiments with single atoms. And in this case, they did with a lot of atoms, and it would be very important from the theoretical point of view to understand better, because it is not completely understood up to now, the collective effects in this system, in this four-way mixing. I know for certain that they are not correctly described, And I would like to learn more about this. Now, concerning the quantum bits, that is the point that I have already worked. Quantum bits arise because even though I told you the system as simple as saying that here you have one state, one state, one state, and one state, in practice you have a lot of states that could participate. You have the hyperfine structure, and in the one should, and we have already done, consider the most important states that are participating in the process, and do the calculation, the standard calculation with the density matrix, and get a description of the quantum bits. I must tell you that we did that, considering 16 levels instead of just the 3 I have told you, the 16 most important levels, and without any adjustment of the curves, we found that the oscillations could be consistent with what is observed. Okay, but there is something I haven't told you that I think that is important. Besides the quantum bits, one would like to know whether theory tells you that this has to be a theta function or not. And I have been a function that has a discontinuity. And I have been looking at the literature, and to be honest, I haven't found a clean description of the system. Kimball, in the beginning, the important Kimball, has been working on that, and all the papers are interested on this and give some interesting points, but nevertheless, never go to the limit when you cannot, when the time is shorter than the optical cycle. No, I have not found any single paper that describes this. What I mean by this, I don't know how long a detector needs to know that a photon has a given frequency. Theoretically, honestly, I don't know how long. Do you have to wait to know that? Do you have to wait the whole cycle? Do you have to wait 10 times the whole cycle? Is it enough to see how the cycle goes? Perhaps you know, but I don't know. And I have found that the theoreticians in general do not know. The other important point is that this step, this transition as a step, involves Markovianity. And you know that in these times, many people is questioning about the possibility of observing some effects that do not correspond to Markovianity to Markovian system in quantum mechanics. So if experiments are done, and at the end you get something that it is not a step function, but something with some inclination up to the higher limits, then I think that the structure of this step function will give you information about Markovianity, how long a detector needs to notice that a photon has a given frequency, and gives you, and also some physics that in this moment we do not know. So the idea continues being the same. Please, experimentalists, measure this with the highest care you can, and perhaps the theoreticians will learn more. We learn more about quantum mechanics. Huh? Okay, so the idea is that we have given an upper bound, just an upper bound to the duration of a quantum jump. This, as I told you, see, there is no limit, and if you can do it better, do it. Okay? So, just to tell you, okay, well, with Silvia we have been working with this subject, but I think that is enough, okay? This is the collaboration. And the work can be found in the archives, okay? This number. Thank you.
So thank you, Rocio, for this very interesting talk. We have time for several questions.
Here's a couple of questions. Mm-hmm. The first one is that in the state 3, well, the atom is not really in an exact line of the energy. No, it has a large width, so it should be reflected, no, in the time of the emission.
No, it's not the same. The width gives you the decay, the gamma you have to put here. And depending on the conditions, and you can introduce Doppler effects, and the decay rate will change. But that is not the same as the racing time, okay? The decay is how probably will the atom will decay or not from one state to the other. Here the question is, how long does it take to go from here to here when it goes? That is different from the decay, how long you have to wait to, with a given probability, see a transition. That is a different question.
Okay. Well, the second question is that you are assuming that you have a planar wave of the laser incident upon the atom, and in principle one should consider photons, no? Wave packets. No? So the structure of the packet could also affect the prediction.
Okay. The laser you are sending here are in the omega the rabbis here. If you introduce a given wave, Gaussian or anything, everything you introduce here.
Yes, but the
in this case, no, this is the frequency of the. There is lacking a T here. Is the frequency of the laser one, and this is the coherent state, the Rabi frequency for the coherent state, and all of them refer to the transition from the ground state to the upper state. And here, these omegas, here you can put a structure, time structure or space structure, anything, and it will modify this. And when you modify this, of course, you will find a different structure for this core in general, and also for these terms, for these terms, okay, for the solutions, but not for the decay, but because the decay is okay. You will put different numbers, but at the end, when you make take the solution, one gets that the solutions here for rho 3G do not have anything but a decay, and it has a structure that goes from 0 to not softly but abrupt. The structure will be the same.
Okay. Any other question? Sebastián.
So you are pointing two lasers to the atom cloud. So which are the characteristics of these two lasers? I mean the light, which are the same lasers or are different between them?
Yes, one has to be centered as 70-80 nanometers. The other must be at 70-76. In practice, this was the tune about, I don't remember, 26 megahertz. And this has to be 2 megahertz up to optimize the possibility of having all the atoms here. It was very nice to see that in the theoretical description that we gave, we found that it had to be 2 megahertz, 2 or 4 megahertz, I don't remember. And later, Alessandro told me, exactly the tuning that Matthias used to optimize that. So the theoretical description going up, we have it at our hands.
Thanks.
So maybe one question on the experimental side. So the technique you are using here is the time-correlated single photon counting, I think. So one problem with this, besides all the problems you mentioned, is that it is intrinsically slow because it's electronic based. So there are other techniques like fluorescence subconversion, which are all optical, and they are faster, I think. So maybe one thing that can be, I mean, this technique is used usually in femtoseconds to measure the decay time of very, very fast particle like excitons or stuff like this. So I guess the response time is much shorter than this electronic stuff, and it might be a better idea to work with.
But what would be the idea? To replace this by, okay, if you want, we can do the experiment with Daniel. We have everything for this side, and we can try this side, okay? And there is also an important point. I was looking in the literature because I don't say that I am the only one that has done or proposed that, okay? So really, during months, I have been looking at the literature, whether someone else has done something like this. And I found a paper, a very nice paper, concerning femtosecond lasers. But in this case, it was very, very interesting, but not so clean. They had an helium atom, and they sent a femtosecond laser. When they sent the femtosecond laser, they were interested in observing how the electron goes and taking a picture of the electron leaving the helium atom. And everything looks very, very soft, but there is a very tiny pump, okay? They published a paper in, of course, an issue, showing that they were observing the photoionization of the helium atom and say nothing. And about a year later, someone said, probably the bump, the small bump we saw here, correspond to the other helium electron that has to reorganize once the helium has gone. And they say, this must be an upper bound to the duration of the jump, okay? But this is a paper, not in the paper, not in the original paper, but it's a comment in a proceeding lost somewhere, okay? In this year, there was a conference for the OSA, and people from the femtosecond side say, we are interested in doing things like that. So yes, perhaps in the femtosecond range, one can try to do things, but I don't see how clean are there, in the sense that here, really, I am looking at the spontaneous decay, and I am just observing a photon that comes, and the noise I may have here is very controlled. And in the other side, one has to look at your idea, Giuseppe, and see whether there is something. I am very interested, no? Because I like it. Okay, thank you.
I don't know if questions or comments. It's a mixture of both. In the theoretical side, I think that the idea of having jumps is necessary. It's necessary, and the experiments probably are showing that there are jumps, although we are the limit of which we still don't know. Because if there were no jumps, then you would have to explain where is the system in the middle. And it would contradict the fact that you have only those allowed states. You will have to introduce other states that are not there. And however, the way we always talk about in quantum mechanics, non-relativistic, there are no jumps in non-relativistic quantum mechanics. They do not exist. We can only calculate eigenstates and eigenenergies and so on. So when we want to address the transitions more quantum mechanically, we have to put photons in the problem. And then we have a terrible problem because photons are completely relativistic, while all of our theory is non-relativistic. And so we come up with theories like this one, that you use the density matrix and these types of master equations, but they have, by hand, put that the transition, as you just showed to us, that the transition is discontinuous, completely discontinuous in this way. So my question is if people have tried to address this problem completely from the point of view of relativistic quantum mechanics, in which you put an atom in relativistic quantum mechanics, which is very hard, and so in which you could calculate the probability and the transition probability and so on and so forth.
Okay.
So the question should be addressed at that level, because at this one, there is no way. Non-relativistic quantum mechanics does not have, not even has transitions.
Okay. The paper was submitted a year ago.
Yeah.
It was partially accepted, but one of the referees said, no, of course, you can do the calculations for how step is this step, and until you show me the best theoretical description of how step is this, it will not be published, okay? Because people in the community will say that this paper says more than it says. Well, I know what I say in my paper, and I can tell you that Kimball, Miloni, that is a friend of mine, by the way, Miloni is a full professor, now retired, and he made his PhD thesis on this problem as a QED problem. Mm-hmm. So the QED description, I have been working on the QED description, but the point is always when you get to the limit, you have to make some assumptions because it is not trivial, and the standard Lindblad description I am giving to you is what you would obtain from QED calculations if you assume that both photons are detected at the same position, whenever the assumption of adiabaticity is done. So it is not true that the point is relativistic, because the relativistic calculation with the addition of adiabatic assumption gives you the Lindblad equations and less than I have showed you, because here I have more things.
The equation is always approximated, always. It's a master equation which you make a lot of assumptions.
No,
so
but I have cleaned the assumptions, and I tell you that the only interesting relevant one corresponds to the adiabaticity that can be shown to be equivalent to Markovianity. So, the idea that you can or not resolve the color of something when the time is shorter than the inverse of the frequency. So I have been working on that during all these 6 months. I have a student working on that. So we can talk of this in detail. Okay? So.
Okay, maybe one more question. Okay, if there are no more questions, we thank Rocio again. And we do a short, I forgot the English word. We have the coffee break now. A short break for coffee break. Thank you. Muy padre, Rocío. Muy bien. Sí, muy padre. Pero entonces Daniel quiere hacer medidas de este tipo también. Okay. Okay.
No sé si se hace
Sí.
porque no nos falta nada.
Claro.
Lo que no, es la canción.
Okay.
No, ya mira, ya. Okay, so welcome back to the last talk of this day of the workshop. So right now we have Professor Santiago Caballero Vanitas. So Santiago got his undergraduate degree in physics at Universidad Tecnológica de Monterrey.
No, ¿qué pasó?
No, sorry.
No.
En el Tecnológico Monterrey. ¿No?
Es el Instituto Tecnológico de Monterrey.
En el instituto, sorry, I didn't write.
Tec de Monterrey, for sure.
In the Tec de Monterrey, I'm sorry.
Sí, no.
I'm sorry,
Está bien.
Now people is awake.
Okay, that's good.
Okay.
Yeah, everybody knows, yeah. Sure.
Next, he got his master degree in the KTH in Sweden. Next, he moved for his PhD in the National University of Australia in Canberra City. Then he came back to Mexico, and now he is a full professor here at the Instituto de Física at UNAM. And today he will talk about feedback-induced quantum phase transitions using weak measurements. Thank you, Santiago.
Thank you, Jorge. Okay, so this talk is going to be a theoretical talk with a lot of equations, so I hope you don't get sleepy too much. Anyways, this work is in collaboration with Igor, which is somewhere in Europe. Basically, you do a permutation of those 3 places, and he's there. And also Denis and Tatiana in St. Petersburg State University. This is, a collection of funding of the Russians, basically, and what we have here in UNAM. And this is work that has been just accepted to be published in PRL like 1 week ago, more or less. And I'm going to tell you more or less the story about this concept of feedback-induced quantum phase transitions using weak measurements. Okay, so basically what I will talk to you about in this talk is I will give you some general motivation on why are we interested in doing this, the origin of the model, and then some effective model that we work with to describe the system, the input and output scheme that we use for the feedback, and what we can do with feedback concerning interactions, phase transitions, and criticality, the relationship it has to some bad models, and how you can do some kernel engineering and some overall conclusions. So this is a theoretical proposal of basically what can be done using feedback at the quantum level in a macroscopic quantum system. So our main motivation is, you have phase transitions in general, so you can have water. This is the triple point of water, so you can have this point here. And then, as you increase the temperature, the system can be from solid to liquid to a gas. And then you can have some other weird stuff happening around. And this is as a function of temperature. And that's how we get, the traditional states of matter that everybody knows. Okay? So then you can go to the quantum limit, and you look at t equals 0 theory about it. We are never at t equals 0, but very close in some experiments. And then you see that there is something called a quantum critical point. A quantum critical point is when you go from one particular configuration of macroscopic ordering in a quantum system, and then it changes drastically to a different one, just to be general about it, right? And this happens at t equals 0, and then depending on temperature, then you can have a regime where you can have some classical critical behavior, and you can have some other things. Why is this interesting? This is interesting because, it is believed that quantum critical points basically control how high temperature superconductivity works. And then, this could give technological advantage. And if we know how these transitions work, then perhaps we can modify them or do something to the material and then be able to achieve, the long-solved dream of having room temperature superconductivity at some point, for example. That's why people are interested. That's one of the interests. right? Here is a nice picture of liquid nitrogen, which we know that we needed to get, superconducting state at high temperature. Okay, so in general, we know that the behavior of any system, any closed system, is fixed by nature. And we know that that leads to having universality classes. Those universality classes, that's why Wilson got the Nobel Prize in 1881, and for doing renormalization group to get something beyond mean field, doing some calculations which was not possible before around the 70s, right? So, and these allowed to increase the notions that we have on macroscopic quantum control and phase transitions. Okay, so the general question is, well, if this is fixed by nature in a closed system, can we change this? Can we change criticality? Can we do something to the system so that we can control it at will? And how can this be done? Okay, so we know in a closed system that's not possible. Near the critical point, we know that the details of the system are not important and they just end up obeying some scaling laws, okay? But can we change these laws, for example? Maybe if we open the system, maybe if we put many VATs. And people have thought about this for some time. And there are ways to change critical exponents with VATs. The thing is that it's incredibly complicated because they have to have a network of different things coupled, and still it's not really clear how you can do it in principle from the basic point of view of even technological point of view. It's incredibly complicated. So what we came up with is with an scheme where you could do this and do that with a classical trick, basically. So for you guys, I will just do a brief review about how you get, for example, the critical exponent in mean field, and then we get all on track, right? So, for example, in mean field, for example, you can write, your Landau free energy, right? And here you have the kinetic energy part, and here you have the so-called mass part, and here you have some interactions. You know that at the critical point, this parameter R should go to 0, and it should be negative, right? And then if you do the maths, right, then you get that the order parameter of the system, which is in this case the population of this mode in 0, goes like a square root of something, okay, of this R. And this R basically goes like the critical coupling, like the difference close to the transition point, okay? And this beta is a critical exponent of the order parameter, and this is 1/2. And this is true for any mean field transition in whichever system you can think of. So if you do mean field in, let's say, spins, you get this. If you do any sort of 5-4 type theory, it will give you the same if you do the mean field, okay? And this happens because basically the free energy can have a non-zero value of the order parameter depending on if this coupling is above the critical coupling, or if it is below the critical coupling, then it's 0, okay? So then basically this is like when you have in a superfluid, it's the same as in the superfluid when you have some coherence, and then you have that you get to occupy macroscopically a state. It's equivalent picture. You can get it, and then in a superfluid system. Okay, and well, there's some reference there. Okay. So now that we know, okay, this is the exponents I'm going to talk about, and this is the idea I'm going to talk about. So as we get close to a critical point, and this is a quantum critical point because the theory is at 0 temperature, then we will get some power law, okay? The question is, can we do something to change this power law and move, for example, this critical parameter? The answer is yes, you can do that, and you can do that with feedback. And by feedback, this is classical feedback. So basically, we will have an open Markovian system with a non-Markovian part, which we will feed into the system, and I will go into the details. So basically, we start with some atoms, right? This is the cloud of atoms here, and they are subject to some potential, right? And then we send some light perpendicular in a plane perpendicular to the atoms, and then they will scatter light. They will scatter light, and then we detect that light. And then, depending on what we detect, then we engineer basically an electronic system, right? And this electronic system, we can control how we feed back again the potential that the atoms will see. This is possible because of the time scales that things happen. I will go a little bit further into the details. So basically, the feedback can give you some Markovianity because there's obviously some history here taking place upon the signals, and you get some nonlinearity, and basically you can get also noise due to the feedback. And this will allow to get a phase transition and to control the phase transition. So what we have here is we have here the light that goes into the system in the cavity. So this is a BEC in a cavity. Here there is not the mirror, but okay. You get the idea. And you get the atomic dynamics here, and then you get some pumps outside. Some pumps through the mirror, which will not be relevant for what I will discuss now afterwards. So basically, we have the kinetic energy. We have the potential that the atoms see, right, in the x direction, right? And we have the light matter coupling that the atoms see, and these are the mode functions that the atoms see. So the mode function of the light here, we take it as a plane wave, right? And it has no structure. But the coupling to the atoms will see some structure, which will be given by the geometrical functions of the light modes that they will see. And these are just the couplings, the regular couplings of light and matter. And this is the atomic, the detuning with respect to the atomic resonance. Okay? So here, if you see, I haven't thought about adding any interactions whatsoever. There are no interactions of the cold atoms. I'm just assuming that it is a BEC. It might be that it's very weakly interacting. And actually, the interactions at this point between the atoms, they will not play a major role, because what I want to see is what actually the feedback can give me. Okay, so basically we have two modes in the BEC. We have the mode at k equals 0, right, the condensate mode, and then we will have a mode, the mode that depends on the modulation that we had here, right? The modulation that we're introducing here, and we can choose the modulation of the mode that we have here to be commensurate with the structure of the light. Okay. So that's this, where is it? Oh yeah. So yeah, here we choose, right, to be in the diffraction maximum. So the atoms will diffract light maximally if we enforce this condition. Okay? So then we have two modes, right? So we have the mode k equals 0, and we have the mode k equals 1 in the x direction. Here, for simplicity, I'm thinking about just an elongated thing, right? That sees that. Of course, you can add more complications and whatnot, but this is not interesting for what we want to do. If you add more details, then we can have obviously more interesting behavior. But in the end of the day, the main idea here is to see what the feedback ends up doing. Okay, and here the population of the two modes equals the number of atoms that we have here. Right, and L is the dimension of the dimension in the x direction of the system. So you can think in terms of about, just being, a very elongated cigar shape type of BEC. Okay. So if you do these approximations and you introduce this wave function, then you can construct, your SU2 operators basically. So the spin in X, the spin in Y, and the spin in Z. Right, and you can reformulate the whole thing, and dropping out some terms that couldn't reach the physics, but anyways, you can get to this effective model. Okay, here what we have is we have again the mode given by the light, right? We have the recoil frequency of the atoms, the recoil energy of the atoms. or frequency, well, because here I just drop h bar anyways. We have some light matter coupling here, you know, and then here we have the feedback. Okay, so this is basically the Rabi model, and we have the decay model, but we have some time-dependent part. Okay, and why we can do this? Because basically the feedback to the electronic signal is of the order of gigahertz. The atoms basically live in kilohertz, and the photons live in megahertz in a good cavity. Okay, so these are well separated scales that we can work with. Okay, so basically here we have the detuning, so which is just, you know, the detuning with respect to the pump and the light what we pump and the wavelength in the cavity. Here is some dispersive shift, which is basically just a constant, right? And here we will have, okay, this is the recoil frequency, right? And this is our effective coupling between the light and the matter, which is given, which just depends on the Rabi frequency of the pump, right? And the detuning. So everything is quite clean, you know, you can see where everything is coming from. And the feedback is given by this time signal, which is proportional to the time signal and some constant, right? That's what we have. Where this is the gain, the feedback gain coefficient, well known in the places where you do where people do control and stuff like that. Okay, so here the idea is basically, so our atoms are like the speaker, right? And then we have the microphone. So we measure the signal and then we loop. So what happens if you do that, which has happening all the time here, like for the past day? If you're very close to the speaker, it starts to beep, right? So because there's feedback because of the amplifier. So in essence, when you think about it in sound, you don't want feedback because feedback is nasty. But here we want to actually use feedback in a positive way. So we want to be able to feedback the signal by using some electronics like we do with sound, right? But here we will do it with light, right? In the end. So we take the signal from the light, we adjust, and then we can see what we can do. Obviously, there will be some tailoring involved, which I will go into more details about that. So this is the input and output. So the idea is basically you have your atoms, right? And then you measure some light, and then you feed that to some electronics device, and then you have a computer, and you can design basically whichever function you want, right? And then you can feed back that signal again by the way that you pump the light. This is feasible, okay? So how do we do it is that this intensity basically depends on this kernel, this H function, right? And depends on this feedback function integrates over time and feedbacks, right? And this is our control signal. So the amplitude that we had here before. So this I here in the Hamiltonian. So basically here we know in light we can detect quadrature, so we detect the light quadrature, and there is some local phase of the local oscillator that we have there, okay? So basically the output signal is going to be made out of the output quadrature is going to be made by some kappa, some loss of photons, some decay rate of photons, and the quadrature of them, right? And we will have some noise. And here we have introduced the noise explicitly. And this noise is Markovian, right? The noise here is Markovian. Of course, you can consider more complicated the scenario, but here we will not do it. Here is just the definition of the matter quadrature. Depending on this design, you either get X or Y or whatever you want, okay? And basically, this will lead you to have a Heisenberg-Langevin equation. So here we have, you know, the equation of motion for the field for the light is going to give by the detuning, and then we will have some coupling with the matter and then with the noise. Okay? So what this kernel here will do basically is will give us a type of interaction. So basically, if we adiabatically eliminate the field from the Heisenberg-Langevin equation, so basically we take the derivative to 0, right, of the expectation value, right, then you can say that that control signal basically is proportional to the output quadrature, and because the output quadrature is proportional to the light in the field, as we eliminate it, it's going to be proportional to the atomic operators, okay? Our spins, our pseudo spins that we introduced, that tell us about if we are in the 0 mode or in the 1 mode, okay? So essentially what we have effectively is this type of interaction just seen by the atoms, by the effective two-level system. So we have this kernel, right? And then we have the spin in X, and then we have the spin in Y, but then this kernel function depends on time, okay? So depending on the time and the way that the feedback is introduced, then we have an interaction in time, okay? That depends on the history of the system itself. And this, you can assume for the sake of simplicity that you have some linear feedback mechanism. Of course, you could do more complicated than that. This is just the most simple case. And you can assume, for example, that you can do a kernel like this, right? Because you can type it in the computer, and you can get this form, right? Which is basically analogous to a long memory type of interaction if this S is very long, is very, very, very small, right? If S is small, then we will have long interaction. Then if it's fast, then it will be short range, right? So you can think in terms of that. You can engineer this, and you can basically up to this point, what we've achieved that basically we have something that can be electronically and computationally designed arbitrarily, which is this kernel, right? We can think about doing several different bad systems, for example, in a single setup, because this is easy to change, right? You just type it in. Right, and then you can think in terms of doing this even more complicated, right? Like a sum of different things, which will give you to new stuff, okay? So, and then you can think in terms of how this interaction, this time retarded interaction basically, is going to interact with spatial-like interactions, okay? So, okay. So what we first looked at is what if we can induce, in fact, these phase transitions with feedback, okay? So basically what we do is we will again go from this thing that it's made in spin language, right? We have Sx as Z, right? The pseudo spin language. And then we will linearize that, right? We will do Holstein-Primakov. We do Holstein-Primakov, then we linearize this, okay? And then we get something that is even simpler, right? To see if even this simple thing can work, okay? So, and then we do the maths, right? And then we get that the conditional signal that we will have is again given by this kernel function that depends on the measurement, the conditional measurement here, right? And then we can look at the dynamics that this will produce depending on how we choose kappa, how we choose the different omegas, right? And then we evolve this, and we evolve this in a very standard way. We use just, what is in this book, which is basically we evolve the conditional probability using the method of quantum trajectories, right? Here is a Wiener noise, right? This is white noise that we have. And then we evolve this master equation. This is the Lane-Bladian part. This is the Hamiltonian part, right? And we set it on, right? And then we check on moving the parameters. So, and then we evaluate and we check how the conditional probability changes from quantum trajectory to quantum trajectory. So, for long-term memory, right, when the exponent of the previous function here is, where is it? Okay, when S is small, right, then we have long memory, and when S is large, then we have short memory, okay? So short memory is like if we would have like a delta function, right? So here we can go like we go from a regime where, in a single quantum trajectory, we see these kind of fluctuations. If we would average over many trajectories, we would see nothing, right? In a single trajectory, we would see these oscillations, right? And then as we get close to some critical point, right, then we start seeing that the frequency increases or decreases depending on the choice of the exponent of the kernel function. And then above the critical point, then we have some slow growth or fast growth. Here, look at the difference in scales, which is important, right? For the measurement of the conditional quadrature that the conditional measurement of the quadrature. So in fact, yeah, we can go from something that will average to 0 to something that won't average that will average to something that is non-zero. Okay, so first, we have phase transition. Okay, so phase transition can be different. Okay, that's check number 2. So what else can we do? Okay, so we can check about the correlators, right? The form of the correlator, which are not that nasty as you would see, right here. So you again eliminate adiabatical. You keep track of the noise that you have here in your equation. You substitute back to your Hamiltonian, and then you get out of that the effective equations of motion of that Holstein-Primakov thing that you had in the beginning, and then you will get this equation for the quadratures of the matter. Okay, which is actually quite simple to understand in a way. So this part here is like an harmonic oscillator, right, with some weird frequency. And this part is some other contribution which depends on time, right, which is controlled by this kernel that we can engineer, and some other parameters that depend basically if we chose on the quadrature choice, right, this theta, which depends on the quadrature, and the kappa, which depends on the number of photons that we're losing from the system. Okay? So we can basically tune these to whichever we want. If you think about that, you can make these signs whatever you want, and then you can, let's say that your kappa is fixed by your mirrors, but your delta, you can make it whatever you want, basically. So it doesn't require, what you can see already here is that the system doesn't require to have a very good cavity. We can even have a lousy cavity and it will still work, the trick, right? And this structure here is similar to the Caldera-Leggett model and even to the spin-Boson model that we have, that I will show you later about that. Okay, and then you can think about if I have the matter quadrature equation, so then I can look at the noise, right? And the noise here, the noise operator, which is this reminding here on the right-hand side, that doesn't depend on the quadrature, is a noise operator. Okay, if you look at the correlation function of the noise, then you can see that this has this normal covariant part because we have this kernel, right? So the noise, in fact, is normal covariant, and we can manipulate it via that kernel. And then if you go and you do the maths and you take some time and many cups of coffee, then you can realize then you can get basically the order parameter of the transition, which would be the square of the correlation function of the quadratures. Okay, and these are related to the Fourier transforms of the noise via this relationship and the quadrature. Okay? Okay. So now, what happens? Well, if you do that, then you can start to look at criticality of what is happening here, and you want to check about what is the limit when I approach the critical point, right, of this order parameter that I have, and you can write it in this nice, useful form, which it tells you the exponent of the thing, of the critical exponent of the order parameter, and here is some shift, just to fit in things, right? And you see that if you change basically the exponent of the kernel, you can get whatever you want. So you can get 3/4, 1.25, 0.9. So you're not, limited, let's say, for 1/2, or in any case to whichever other nature given critical exponent you can have. You can do it whatever. So as you change S, the critical exponent can go from 0, it's not really 0 here, so it's some small value, to 1, and then if you keep pushing it here, I think if I remember correctly from Dennis' simulation, by the way, Dennis did the simulations on Tatiana too, about these quantum trajectories, and that's what you get, right? So, and you can manipulate where the critical point actually occurs, because you can change this, the kappa and the c theta, right? Depends on the choice of your quadrature. So you can even change, when it happens and how it happens. So full tuning is possible. And just to give an example, for example, if you choose just the regular ohmic BAT type equivalent, which would be choosing the exponent to 1, then you get, and here you measure instead of the x quadrature, the operator is x, so you would see nicely, the well-known behavior that you will get in the quantum phase transition of this thing. Okay, so what is the relationship we have to BAT models? Okay, to BAT models, so if you remember, what we have is something that has this kind of structure, right? And here it's not fairly obvious yet. But still, this is a decay model with so many BATs, right? So that's why it's called spin boson model, because you have here the light, and you have your two-level system, right? So if you linearize this, you get the Caldera-Leggett model. And if you do the equations of motions for the quadrature of this thing, then you get basically exactly the same structure that we had before in the beginning. So we have some frequency, right? Some frequency of our harmonic oscillator, which in our case was more complicated, and it wasn't fixed just by the recoil energy, but we can actually make it whatever we want. And then we have again the feedback, the function here, beta, is like the feedback kernel, and the omega function here would be equivalent to the Fourier transform of our kernel function. Roughly. The only difference here is that this F here, this Markovian, this noise operator in the case of the Caldera-Leggett model is that it's Markovian. So in a way, we are looking at a system that is a generalization of this, which can accommodate whatever we want on this, and we can introduce many, many different BATs. And we can simulate, basically, with a single device, many, many different systems. So, what else can we do? Okay, we can do some more kernel engineering, right? And for example, if you do the kernel like a delta function, what you will get is basically the well-known Lipkin-Meshok-Lick model of nuclear physics, which is just printed here, which is the effective Hamiltonian that you get is something like this. In the absence of feedback, you get exactly something very similar to this too. So basically, you can tune this G to whichever value you want. Okay, that's the simplest case that you can have. You can obviously have the finite range or finite range in time version of these, which will be more complicated, of course. But then you can also think about having a discrete type thing, right? So you would have some delta function peak that it's somehow periodic in time, right? You can do that. You can engineer that. It's not a problem in the machine. And then you can have this power law behavior, which you can do easily. And then you will have some sort of finite range in time stroboscopic type of interaction. That's what you can get out, in principle. Oh, oops. Okay. So, and this is the people that work in this with me, Igor and Denise and Tatiana, and this is the funding people in Europe, basically. And this is the people in UNAM, right? My senior collaborators, all of them here. Just Nieves was sad and didn't send me a picture, but she's there. Okay. And my students here, and this is what we do. We do quantum matter, basically. And for conclusions, so I hope I have been able to convince you that using classical feedback and weak measurement allows to achieve a new kind of quantum simulator. We think it's a powerful one. That it is possible to tailor and do whatever you want using feedback, quantum critical behavior. And the other thing is that this is classical feedback. Of course, you could think in terms of doing quantum feedback, and then probably you will get some other interesting things. There are new possibilities that you could use in this system. You could have finite range in time type of interactions that could trigger, for example, the formation of a structure in space, breaking time symmetry, for example. And this could be useful for tailoring problems in macroscopic systems, even in cold gases, for example, design of a particular thing that you want to occur in time, right? And then see it stroboscopically. And well, we can use this also as a machine to do the simulation of very complicated bad systems in a single go. And thank you.
Thank you, Santiago, for this very nice talk. We have time for questions.
Hi, could you explain again the use of the weak measurements in your work?
What do you mean by the use?
Where in which part did you use the weak
Oh,
measurements?
here, look, if we go back, here. So here, you know, here we measure, by this operator F, we actually measure the quadrature of the light. So basically we measure the real part of the amplitude of the light that is scattered from the atoms with some detector, right? I don't care about the details of the detector. I just need to have a very good detector and have not that many losses. And we actually showed that even if the losses are bad, like with the kappa, it doesn't really matter. So you can always fiddle around with it. See.
More questions?
And what are the critical exponents that you get with this procedure, this scheme, the feedback transition?
We can get whatever value that we want. So you can, if you want, let's say, if you would want to have the ones for the Ising universality class, you can get them. You want 1D, 2D, 3D, whichever D you want, you can get them.
But what about the physical system that your equations are representing?
Okay, basically this is a hybrid system, right? Well, it's a hybrid system which is, it has an electronic part, right? It has some light part, right? And has some matter part. Okay, so I have 3 different things put together in a cocktail, and with that I can achieve some things in the matter that don't happen under regular conditions. Okay, so if that answers your question. So the physical system that we have is you have the cold atoms, and awfully cold in a BEC inside a cavity, and then you have light pumping to the system at 90 degrees angle. So you have the atoms here, you put it like this, and then you detect the light that the atoms emit, and you choose the conditions of the mode that lives there so that the diffraction of the light that you put in is maximal. And then you change in time the amplitude of the cradle that the atoms see. So basically you're doing it like this, right? You're moving them like this at a particular frequency and with a particular pattern in time. And then you detect that. You detect that, and then you, depending on what you want of your detectors and what you design for the kernel to actually to feed it back, then it will change. And that's why you can, so because the system is open and non-Markovian, so it's dissipative, non-Markovian, and quantum. So because if you combine those 3 things, then you can get this.
Any other question? Diego.
So you claim that you can choose any critical exponent you want from the set of the simulation, right? So you claim that you can choose any critical exponent you want, but my question is, what happens with the scaling relations of the critical exponents, and what happens to the other exponents of the critical transition?
Okay, this is just one of them. Okay, this is just, I just thought about the one that is the order parameter, right? So, but then you have the correlation one, and then you have the dynamical one. So it depends on a case-by-case basis. So to tell you the truth, we haven't had the time to compute that yet, okay? But most likely, from what people have done in quantum open systems, in system with bats, you can have that, for example, the dynamical exponent of, let's say, the quantum part and the classical part, they might not be the same, for example. So then the effective field theory that you get in the end gets to be classical, right? It's still driven by quantum fluctuations, but it's classical, the theory. So that's one possibility, that they are not, that there are some parts of the system, let's say the ones that are quantum, they have one exponent and the classical one have a different one. It could be that they are the same, for example. Then there's also the way that the correlations behave. So we just started to see what you can do with this, but at least, for example, this critical exponent you can change to whichever value you want, okay? Obviously, the dynamical one, well, might be tricky, right? Because the dynamical one tells you about the difference between space and time. And then if you fiddle around with the way space and time, the way that the space is doing it, and the way that if you're fiddling around with the way that time scales, and then you include, again, for example, interactions with the space, I don't know what's going to come out, to be honest. But probably you can also move them. I don't know with which flexibility.
More questions? So I have one.
Yeah.
So essentially you can invent a system that has a universality class that do not exist in nature, right?
Yeah, that's what you can do. Because you can.
Because you can.
Yes.
That's it. Okay.
Okay.
Thank you. So, any other question? Okay, Alexis.
Could you engineer feedback but with fermions, or it's irrelevant?
Oh, you can have, I mean, this is just, just a simple example. But if you can do it with bosons, you can do it with fermions, you can do it with ions, you can do it with whatever you want. Basically, just, obviously, the model obviously is not going to be this one, the starting model, but you can do it with whichever system you want. Yeah. In principle, this is just an example, the most simple example we could think of. I invite you, go ahead, you can look at many more different examples. And of course it will give you different things, but even at this level, this simple one without having interactions gives you something. Okay?
Any more questions? Okay, if there are no more questions, we acknowledge the speaker. Thank you. Thank you. And we finish with the workshop for today. I wait you here tomorrow at 10 o'clock in the morning. Thank you.